But let me take a break from that and talk about this half-life rule, which is purely a quantum mechanical effect. And so here we are getting into the heart of quantum mechanics with the half-life rule. That's the following way. I am older than most of you. I will outlive some of you, but most of you will outlive me. The fact is, as I get older, my life expectancy gets shorter and shorter. I'm now 62 years old, and my life expectancy is probably another 20, 25 years. For someone who is, so that, I'm getting older. The remarkable thing about radioactivity is it doesn't work that way. When an atom is sitting around waiting to explode, boom, it's gone. Suppose you create a large number of atoms. Suppose you make plutonium, and you have this plutonium here, and you wait. And after about 24,000 years, half of the plutonium would have exploded. And you have this half left. So is it now the old man? Is it something with not much life left? So you make some new plutonium, and you compare it to the old plutonium. And they behave identically. This one isn't aged. In another 24,000 years, half of it will decay, half of this will decay. And you take the part that's left, 1/4 of the original. And it behaves like brand new plutonium. This stuff doesn't age. So what is going on here? The fact is, what's going on here is so mysterious that we just think of it as a new law of physics. It's not something you explain in terms of other things. There's no mechanism inside that's click, tick, 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 ticking. What happens is if you have an atom of plutonium or uranium or potassium-40 or carbon-14, it has some probability of decaying every second. And that doesn't change. For carbon-14, after 5,730 years, the probability that it would have exploded is 50%. That's called the half-life. But if it hasn't exploded, it's not going to then explode in the next 5,000 years. It only has a 50% probability of exploding. This is truly mysterious and amazing. And nobody has been able to explain this in terms of anything else, and most people have given up trying. This is the way the world of quantum mechanics works. It's a probabilistic thing. So if you start off with 1028 atoms, on the average, after one half-life, it'd be down to half of that, to 512. If you wait another half-life, you're down to 256 on average. Sometimes it'll be more, sometimes less. It's a square root rule there. You wait another half-life, and it's down to 128 on the average. Then you wait another half-life, and it goes half, 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 half. Now, after about, I don't know, maybe after about 60 half-lives, even if you start off with Avogadro's number, 6 times 10 to the 23rd, and then you're down to 3 times 10 to the 23rd, and then 1.5 times 10 to the 23rd, and you do that. But if you do that for 60 half-lives, you're down to 1. Now, what happens when you have 1? Will it decay or won't it? It's only a probability. This is really strange. It's not as if there's something in there, a little clock that tells it. It's not like I'm using up my, all of my energy and eventually run out and my cells are slowly dying. There's nothing like that going on. These old particles are identical to the new particles. And we have ways of measuring identical by doing a thing called an interference measurement. And it's very, very strange. We'll talk a lot more about this as we get to quantum mechanics, but this is a real quantum mechanical effect. And not only is it not understood, but most people think we never will understand it, because this is the fundamental principle of quantum mechanics. This is the principle on which everything else is based. And when you start with a first principle, you don't explain it in terms of something else. You try to explain it in terms of a little mechanical thing going inside the nucleus. There aren't any mechanical things going inside the nucleus. Things don't work with little mechanical tools down at that level. Things work quantum mechanically with wave functions down at that level. And this is a fundamental property of wave functions, so we're never going to understand it. Very strange, the half-life rule. You take two particles which are truly identical, and they decay at different times. Now, one of the things that I find fascinating about this is if two things, this is an absence of causality. These two things are identical. They're treated in every way. They're produced together. They're identical twins in the identical environment, and they will decay at different times. So the decay is not causal. You can still say something about it. You say, oh, it's very likely it will decay within a few half-lives. So we have a principle that allows us to discuss the statistics, but not the individual cases. Now, back in the 1800s, people, when physics was really going strong, they used physics as an example of how we are probably just chemicals that are reacting to input. And if we could write down all the equations of the body, we would be able to predict whether I'm going to hit the table with my hand or not. Okay? And that's predictable if you really knew all the atoms and how they were moving and so on. Now, that was based on the fact that physics looked causal. And hey, maybe our own free will is just a big illusion, which to a large part it is, as I've learned. The things I pick on my own, I then later figure out who influenced me to do that. So we do have some illusion of free will. But do we have no free will? People used to take from physics that everything is causal, and therefore free will could be an illusion. And many people who saw all the power of physics, hey, all the things you can make out of it, you know, steam engines and later atomic bombs. Physics seems to work better than religion, so let's take on physics as our new religion, believe that this is what everything is. And then, with the discovery of radioactivity and with the discoveries of quantum mechanics, the basic assumption that was used in that logic is totally wrong. Physics is not causal. There are major things that happen like radioactive decay, and at the atomic level, many things behave in this way. You can only talk about probabilities. There is no causality here. So what has been demolished was the 19th century argument against free will. Does that mean we have free will? No. It just means that the one powerful argument against it is completely demolished. This is something that a little bit of physics relating to other subjects that I think everybody should know. So that's the half-life rule. We're going to find next week that there's something opposite, the doubling rule. If you double, you can go from one atom to 2, 4, 8, 6, and 32, 64, 128, 256, and so on up, and get up to Avogadro's number in about 60 to 80 doubling times. And that's the basis of the chain reaction, which is used for everything from the atomic explosion to PCR in biology, which is what's probably the most important invention in modern biology, is PCR, the polymerase chain reaction that allows us to measure DNA very conveniently. So this chain reaction is the doubling rule, getting from small numbers to very big ones. The opposite is the half-life rule, where the numbers get down. You know, the probability of surviving one half-life is 1/2. The probability of surviving 2, multiply that by 1/2. Of 3, multiply that by 1/2. 4, multiply that by 1/2. Generally, it's 1 over 2 to the n, where n is the number of half-lives. And that number can get small very quickly. You don't believe it? Multiply 0.5 by itself on your computer or calculator or spreadsheet and just see how small it goes. So pretty soon, the probability is this thing will have decayed. You're not going to have something around 30 half-lives later. It's really gone. So it doesn't have free will. Well, except on little decisions. Something like that. So I talked about ionizing and colliding. Of these radiations, electrons, helium nuclei and helium balloons, gamma rays, these are penetrating. X-rays are also penetrating. They're not quite as energetic. They are 1,000 electron volts, where gamma, these are like 1,000, where these are like 1,000,000. We can make an X-ray in an interesting way. What you do is you take an electron, an energetic electron. This is how you make an X-ray. You take an energetic electron with maybe 20,000 electron volts of energy. That's 20,000 times as much as a typical atom has. To give it this energy, you have to use electricity. We'll talk about that after the midterm. But you get this thing going really fast, and then you run it into a piece of tungsten or other heavy metal. When it gets to the tungsten, this electron will stop very suddenly because of the nuclei in the tungsten have very positive charge, and they will get this thing and they'll grab it. When you suddenly change the velocity of an electron, it tends to emit a gamma ray. So the gamma rays will come out like this. You're basically shaking the electron. We'll talk a lot more about this when we get to radio waves. And so the gamma ray comes out like this. It's not a gamma ray, it's an X-ray. And so it will have an energy typical to this, generally a little bit smaller, maybe 10,000 electron volts. Remember, visible light has an energy of about 2 electron volts. This is 10,000. This is still light, but it behaves very differently. When it passes through you, it has so much energy that it tends not to be stopped by conductors. It gets right through, gets stopped by calcium, making a shadow. When you're getting a tooth X-ray, what they do is they put your tooth here. So here's your tooth.